next, getting into Anylogic. As a company is concerned, Anylogic is there for last so many years, a decade or so in the market. And this company has been founded by two people. One is Andrew, and second person is Timothy. He's a founder of Anylogic company. And so you understand. So we want to bring the right people in front of you. So, and later, he's the sole responsible person for the Anylogistics product. And so you can ask or any questions on Anylogistics because he's a man behind Anylogistics completely. Sales, support, development, everything. He's a so and so. He has a beautiful team working for Anylogistics. So under part of Anylogic umbrella. And the next person we have is Andrew. So Andrew is responsible for the development of transportation optimization module inside Anylogistics. And you can also see he's also very authentic. Probably he's a right person to support Timothy in this session. So Timothy, it's for you. So and Anylogic is a big, the product-wise or company-wise, the fastest growing company. And Anylogic as a product, it is having the maximum share in the process simulation market, around 35% market in the globe. And now Anylogistics in the chase. Let's hope that we are going to prove that. Yeah.
Rajiv, thank you for introduction. Yeah, I have one. Yeah. So I am glad to see all of you here today. And before I start, I actually would like to make one, I think, very important note. Yeah. For me, English is not a native language. So if you do not understand something I'm saying, yeah, please feel free to raise your hand and ask your question. And the second problem for me right now, that I'm still getting used to Indian pronunciation. Yeah, I'm improving with that, but still experience some problems to understand some words. So please forgive me if I'll ask you to repeat the question. Just again, that's because of it needs some time to get used to that kind of pronunciation. Sorry for that. So with that said, so let's start with our seminar. So sorry. Yeah. This is the agenda for today's seminar. So I'll start with the Anylogistics introduction, and the presentation I'll do will be mixed together with a demo. So I'll show you some slides, then demo the product, the models, how they work, and what you can do with those models. And again, after each demonstration session, so again, feel free to raise your hand and ask questions. So at the end, I'll show you a couple of case studies. So unfortunately, yeah, when we were working on that session, or on that section, we were trying to get a permission from the companies which work in India to show the cases here. And unfortunately, the company who work here doesn't give us a permission to do so. And since the most probably companies in the world, I mean, at least European, American, have some connections with India, we did not manage to get the permission from them. Fortunately, well, it's not actually fortunately, but yeah, fortunately Russia does not have so many connections with India, so we got the permission from a couple of Russian companies and from Deloitte to show the project they did there. So, and the case studies I'll show you today, two of them, they're both from Russia. So, but in any case, I think you'll get a good understanding what you can do with the product and how you may benefit from both, like the network optimization and dynamic simulation, part of Anylogistics. So, when you deal with a supply chain, there are a lot of problems you have to answer. For example, where to locate the facilities, what should be the flows between the facilities, how much product you have to store and where, what the inventory policies you have to use, what should be your transportation policies to say what to do if you, let's say, buy another company and want to merge two supply chains in one, how to do that, what is the risk associated with your supply chain. So basically to say there are a lot of questions the supply chain manager has to answer in order to manage the supply chain effectively and efficiently. So if you look at the methods which are being used, so if you try to map those problems to make, let's say, correspondence between the level of detail which is needed to solve a problem and the problems which can be solved with that level of details, we'll get the following picture. For example, at the high abstraction level, when you consider only things like locations, you represent your supply chain as a set of flows, as a set of linear dependencies. So you assume that all the parameters are aggregated, let's say the demand, lead time, and so on. So in this case, that's the problem you might address. For example, where to build your distribution centers or factories, so the facilities basically to say, where to stock the products, what will be the flows between the facilities. Also, you may do actually some fleet estimation, some rough fleet estimation in that case. And also do master planning. Master planning is about how much, let's say, you have to produce or you have to store at which facility per period. Period may be like 1 week, month, 1 year, whatever you want. Then, if you take more things into consideration, like real time, real dynamics, you take into account randomness, you take into account network processes, logic, resources, then you might address even more problems. For example, you may do like transportation planning, you may do risk analysis, because of risk is always associated with the time and randomness. You may estimate like the inventory policies and sourcing policies, because of, again, they depend on time. So you may also do some resources planning, more accurate one, because of, again, the resources always depends on time, depend on time. So then, if you take into account even more details like how your supply chain objects, factories, distribution centers, fleet works inside, so only the more problems you may address again. You may see how that inside for walls logic may influence your network level, how it works with your supply chain, how actually, and estimate how they just fit each other. I mean, this inside for walls logic and network level. So if we try to draw here this shape which would represent the number of supply chain problems which can be solved at different level of abstraction, we'll get the shape like that, which basically says that the more detail you take into account, the more problems you may address. Again, this shape represents the number of supply chain problems you may address at each level. So, methods which are being used to address different supply chain problems. Can you guess what's the most popular methods which is being used to solve supply chain problems? Which one? No. You are close, but actually Excel. You probably all work with Excel, right? And that's, you always start with Excel. You always first try to solve your problem with Excel, and only if it doesn't work, then you switch to another methods, right? So we also know all the advantages and disadvantages of the Excel. So in that presentation, I actually will not talk much about that, and mostly focus on the following two. One of them is analytical optimization, and the second one is a dynamic simulation. So, because as we know, Excel works perfectly for the a small size of supply chain problems, but once you really deal with a large problems, let's say, yeah, it doesn't work anymore. But again, it's unique if you want to do some simple calculations. Any question on that? I'm making sense? Great. So now let's talk a bit about the methods I just mentioned. So first, let's start with the analytical modeling. So what kind of problems analytical modeling allows you to address? First, this is what is called supply chain design or greenfield analysis. Basically, this is to answer the questions like where to locate the facilities, what should be the flows between the facilities, and also you may identify the throughput of the facilities. Please don't confuse with the capacity. We'll talk about that a bit later. Master planning per period, I already mentioned that. So that's what allows you to plan how much to produce and store per period, let's say per week or per month at the facility. And then it also allows you to do some transportation optimization. Basically to say, if you try to generalize the problems which you address with the analytical models, all of them answer the question, basically, what's the plan? And if we come back to the model structure, if you consider like the actual supply chain, which has time, products, orders, some transportation rule resources, and so on inside, when you do this modeling with the analytical modeling, you solely need a person who can do this mapping, let's say from this actual world to the analytical one. And this person actually mapped that, describe the actual supply chain using that terminology. So they describe the time as a period. Again, there is a difference between time and period, so we may talk about that later. So they describe all the products, flows, resources as, sorry, not flows, like products, orders, resources as a flows. In the case of analytical modeling, and also facilities are actually represented as a solely location and throughput, which may come through these facilities within a period. So there is no way to take into account, in case of analytical modeling, things like randomness, network level logic and processes, as well as inside four walls logic and processes. So, and what is important to remember, that this is optimization. So once you have this model and you solve this analytical model, you get the best result, or at least very close to the best one. So, by the way, how many of you are familiar with the dynamic simulation? Could you please raise your hand? Wow, very few. Okay, so, I'll explain later why I'm just focusing on that, because in dynamic simulation, it's different. This is not optimization. So, key points of analytical modeling. Again, analytical modeling is well equipped to solve large-scale problems. The disadvantage that analytical modeling is not able to precisely describe the reality, because of to be able to map your actual supply chain problem to that analytical world, you have to do some abstractions. You have to abstract from that kind of details which cannot be described with analytical equations. For example, there is no way to take into account things, again, like the dynamics, the time, I mean the actual time, not the periods, randomness, and things like logic. I mean, that may be operating logic, like inside four walls logic, it doesn't matter. So, and you may actually consider that approach as a black box because of actually two reasons mostly. One of them that you never know actually how the solver, well, probably if you program that solver, maybe you know, but in the most cases you don't know how the solver works inside. If you get some infeasible result, or let's say a solver cannot find a solution for the problem you defined, you may only guess why that solution isn't feasible. Certainly ALX or other product may just recommend you to do something to make it feasible, but actually ALX doesn't know about the logic, or I mean the logic behind your thinking when you just created that model. So yeah, it may say, okay, please consider increased demand here or decreased demand here, something like that. But in any case, that's up to you to guess why Cplex or ALX cannot find a solution for the problem you defined. Yeah, let's look at some examples. Sorry. No, I think I have to just exit this small end. So this is any logistics welcome page. I already opened some examples for you. By the way, can you see this on the TVs? Yes? Yes? Okay, good. So now we are connecting to the database. ALX has a database which comes together with any logistics. It's like a file-based database which you may use by default. But as practice shows, actually in the most cases, you will prefer to use the database you have in your company. It may be Oracle, MySQL, or SQL Server. So you may actually connect to any database you want to. So I'll just very briefly describe the user interface. So that's the different type of scenarios you have in any logistics. This is greenfield analysis, network optimization, simulation, transport optimization. That's the tables to define the supply chain or define the scenario. So that's the actions you may do with a selected scenario. For example, edit data, run some experiments, and then analyze the results in output tables. For example, that's if you select data, that will be input tables. If you select an experiment, that's output tables. So, and it's only if when you develop your model, you may look at the map. I mean, where the objects of your supply chain are located. Also, you may look at the logical structure of your supply chain if you want to. So, yeah. Well, that's very briefly how it works. Yeah, and this bottom is to show the connections between the objects. So, again, with that said, let's start with the examples. This is a simple greenfield analysis, so which is about locating the facilities. So the greenfield, that's greenfield analysis. Let's say the standard greenfield analysis does not take into account the real roads. So it just measures the distance as a crow flies. So that's why if you do this greenfield, in some cases, you may find out that greenfield suggests you to put the distribution center in the middle of the sea. For example, if you will do that greenfield for, let's say, the country like Indonesia, where there are a lot of islands, with a high probability it will suggest you to put the distribution center is somewhere in the sea or in the ocean. So that's why you have to be careful when you use this type of analysis. But it also has a great advantage because you have to define very basic information to run it. You just define I'll just show you. Yeah? You just define the customers, demand, and products, and that's all. So, and using only that information, ALX will do the calculations where to locate the facilities. So let's come back to the results. So if you look at the results, so there is so sorry, can you see the tables? Yeah. Okay.
For me, it's too small. If you can
Yeah, I'll just try to. I'll try to use this one. Is it better? Yeah, it's a bit more difficult to show, but yeah, I'll try. I'll do my best. So, for example, here you may look at the product flows. Oops, here they are. So, and this is just an example of one of them, like from the GFADC to that customer, that product, in that period, so you will have to deliver that, you have to ship that amount of goods. And that's the distance between those points. This is some cost, flow cost estimation. So another thing you may look at, this is, it's called distance coverage by demand. So it says how much of demand are satisfied within which distance. For example, in that case, in the case of GFADC2, so it says that 10% of the demand are satisfied within 38 kilometers. So, and 100% of the demand are satisfied within 100 kilometers. And also there is just opposite statistics when you may look at distance, like 10 kilometers, 20 kilometers, 30 kilometers, and how much of demand is satisfied within this distance around your facility. That's the statistics you have when you run greenfield analysis. So certainly, if you want to find out like the next level in your supply chain, let's say now we just used the customers to calculate the locations for the distribution center, but there can be a next question. Okay, I have the distribution centers. Now I want to find out a factory, where to locate a factory or like a super distribution center. Then I do the following. I'll just show you another experiment that's called the same model. So, but it already has this model. It already has these distribution centers defined, and in experiment settings, you just say that okay, I want to find a super distribution center. Find the facility, let's say, for all the sites in the system. So, again, using that control, what you can do, you may just switch on the facilities for which you try to find this super factory or super distribution center. So if I run it, yeah. So you see, that's the distribution, like a super DC, which was suggested by the system. Again, by the way, if we just look at the connections, so that's the connections between the facilities, and as you see, all the connections here, they're straight. Again, that's why that's because we do not take into account the real roads here. again, we may look at the structure of that. See, that's the structure for our supply chain. Any question on that experiment? Okay, so another one which I want to show you, this is not like a standard or classic greenfield analysis. In that example, we use another experiment which was which is not standard. Basically, how it works. So you may define don't like to work with magnifier. Yeah, so how it works. Inside ALX, there is the database with the population for the cities worldwide. And when you're considering to build a DC or rent a DC, you probably will not consider like to put this somewhere in the mountains. You probably will consider some real locations where you may just hire workers to which will work at your distribution center. So, and here you may define the population of the cities which you consider. Basically, it means you're considering cities with a population 50,000 and more. So, yeah, I'll just run that example. So, and what this experiment takes longer than greenfield analysis because of it's already a mixed integer programming problem, MIP. But again, the huge difference with the previous experiment that it takes into account real roads. You see that's not like a straight connections. Yeah, it uses real roads to do all the calculations. And we may just filter objects. Let's see. Yeah, you see, that's. So you may zoom in to see a particular locations. So, yes. Let's switch back to.
Excuse me.
Yep.
I have a question here. What's
Yep,
your
please.
source for the real road distance data?
Source, yeah, it takes from the OpenStreet map.
OpenStreet.
Yeah, basically they run on our own servers in the internet, so they update it regularly. So, and all the distances and routes, so they are taken from there.
And more or less they are available for all the worldwide.
Yes, for worldwide, yeah.
Stored within any logic, or I'm querying it in real time?
Sorry, could you please
Querying the distances for the roads in real time, or is it stored within the ALX database?
No, they store it at the server. So we have like this is OpenStreet map. So that's similar to Google. So and all the data, I mean about the distance, the roads, they download it from that server. So it's not Excel file.
So it is stored within the product.
No, it's online.
Okay.
It's online, yeah. Oh? Cache. Oh, yeah. And yeah, just Andrei reminded me to say that we also have a cache. So if you download those routes and do the experiments with your model, the ALX will use the routes which are cached and will just request them again only in the case something was changed. Sorry, I also was going to show you a couple more examples. So the examples I just showed you, that was about the greenfield analysis. Yeah, now I would like to demo you how network optimization works. Again, this is, oh, excuse me. It's difficult to work with a magnifier. So that's a global supply chain. So, and the idea behind that optimization problem is to find out where to put the distribution centers. So again, take into account everything, the cost of the flows, the railroads, and so on. So by default, all those objects, they are connected to each other. So it may take some time actually to download all the routes because there are just a lot of them here. So we probably may not wait for that. So. Oh, sorry. Yeah. Okay. Yeah. Yeah. You see, at the moment, they're just everything connected to everything. So. When we run that experiment, yeah, oh, I'll just show you that. It downloads the routes. Yeah? Yeah, could you please use microphone to ask your question?
So when you are optimizing the network across continents, so how you are like deciding about the ship route or flight?
Yeah, well, you may define the cost for different connections. For example, you may say that between the continents you ship the goods, you may ship the goods with the vessels. So if you use vessels, that will be the price per, I don't know, per container or per cubic meter, or per product, depending on which unit you want to use. So, and within the continent, you use other type of vehicle, which you also have to define. For example, it may be truck or lorry or railways. Again, it depends on what you want to, how you want to transport your product. So, and when you run the optimization, ALX will take into account all those different routes and costs associated with the different type of fleets or routes.
So, because in the map you showed it, it showed me the distance by how it moves by truck, but we didn't get any, any such network for liner movement. So,
you did not tell. So I'm not sure I understand. Yeah.
Okay.
Basically, it's asking you are not defining any ship or road or railways when you are doing this analysis for greenfield.
For greenfield, yes, you cannot take that into account. In the case of greenfield, you just assume that you pay, let's say, $1 to ship 1 cubic meter of your product. That's only thing you may take into account when you do greenfield analysis. But when you do network optimization, you already may take into account the type of vehicles you use. You may associate like a different cost with different type of vehicles as well as with a different type of products. Because in case of greenfield, in spite of we may have, let's say, 1,000 products, but the cost will be always measured, let's say, like dollars per cubic meter, not per product. Again, because greenfield use always needs to use that aggregated information. So, yeah, that's basically the output which is provided by Ciplex. Yeah, by the way, Ciplex, this is a leading probably solver from IBM which is built in ALX. So that's the result we got. So the most time actually, as you saw, was required to download all the routes. So, and that's the configuration which is suggested by the product. So we may just switch off customers to see the structure. So you see we have like the direct lines between the continents. That was the question, right? And we have the roads inside the continents. Any question on that example? Yeah, here you may look at different statistics again, just analyze product flows. You may do, by the way, filtering here. For example, I want to look at, let's say, sorry. Yeah, you may just type something here, and then it will filter all the values in the row, in the column, sorry, below. So, and that's a simple example of master planning. Just run that experiment. So, by the way, before the experiment is run, so ALX verified the scenario data. That's why you saw that window, which dialog, sorry, which was saying like a verification. So, and if model structure is correct, then it runs optimization. So, this is again the supply chain structure, and plus you may also look at the products by periods. You see, we may look at these tables to analyze how much products, let's say in period month 1, we have to ship from Orléans to site 3. So, and when this product has to arrive. So, and we have that table for each month in the year. Any question on that optimization side? No? Okay. Sorry, I'll switch off this magnify mode. Yeah. Oh, great. Good. What is dynamic simulation? So, since the most of you are not familiar with the dynamic simulation, so will try to explain you very briefly what it is and how it works. Again, feel free to ask me any question you have, while I'll describe you that slide. So, what is dynamic simulation? First, the simulation model is described as a set of rules. What does it mean? Let's say we have, like in our supply chain, we have customer, we have distribution center, we have a factory and supplier. What we do next? We say in our model that customer place orders for 300 units every day, 4 days a week. So we describe the customer behavior. Then we go to factory and say, okay, initial inventory is 3,000 units. So if inventory below 2,000, then it has to order batch of 300 units from the factory. For the factory, we will say, okay, if factory has the orders for 300 units, it starts production. So if raw materials stock drops to 100, let's say, cubic meters, then we have to order another 300 cubic meters of raw materials from the supplier. And for the supplier, we may say, okay, if supplier workers are on strike, supplier will not process any order, for example. So then, again, that's the model. We just define the behavior of our supply chain. Then the process of execution of that simulation model, how it works. This is a modeling time. So let's say we have a day 1. It means the customer, we just start our simulation. The customer, according to that rule, customer placed the order for 300 units. What will happen day 2? Say it again, sorry? Correct. Day 2, we'll order another 300 units. Day 3, another 300 units. Right? Day 4, another 300 units. What will happen on day 5? Sorry? You see, we just order the products here, right? Here we have the initial inventory 3,000. We already ordered 1,200. So we drop below those 2,000, right? Those, on day 5, since our stock is below 2,000, we will order 3,000 units from the factory. Day 6, when factory receives that order, factory starts production. Because of, again, it has order for 300 units. Does it make sense? Good. Then, let's say on day 7, our stock is dropped below, our raw material stock dropped below 100 cubic meters. What will happen? Correct. But our supply is on strike and do not process any order, for example. See, again, this is very briefly how it works, what means that simulation process. Then, what is the output of the dynamic simulation model? That's probably the most important thing to understand. This is actually the behavior of your system in time. Because of, as an output of that simulation process, what you get the dynamic, for example, of the orders you placed. Like, for each day, you know how much orders were placed. Then, at the distribution center, you may look at the inventory dynamics for each day you modeled, right? For the factory, for example, you may look at how much product you ship every day or you produce every day. So, again, this is not an optimal result. This is how your supply chain works, how it operates in time. That's important difference. Is it clear, more or less? Okay, good. So, we were often, yeah, well, we are coming actually, we are coming from dynamic simulation world. Our another product is AnyLogic, which is general purpose dynamic simulation software. And that's why we are pretty comfortable with the dynamic simulation. But once we started to develop ALX, we discovered that the most of supply chain people are well familiar with the network optimization, but knows almost nothing about dynamic simulation. They did not understand how they may use it. And in order to explain when you have to use the dynamic simulation, I was trying to find some resources from that community, from the supply chain community, to explain why you need this. And I think that's a pretty good explanation, which was given in one of the books. This is Towards Supply Chain Risk Analytics. So basically it says that if the level of details vice versa, let's say, if the problem you're trying to solve doesn't require you to go deep into details, then use analytical methods. Use optimization, just because with optimization you get the best result. But once you face with a problem which cannot be mapped to that analytical world, because of the complexity, which again arises from the time dependence, some randomness, some interacting effects or logic basically behind your supply chain, then you have to go for dynamic simulation. What kind of problems can be addressed with the dynamic simulation? For example, this is supply chain examination or implementation. Because let's say you design the plan with a network optimization, you know how much to produce each month, but then the question, how to implement that? What should be your inventory policies inside? How your conveyor system should work inside? So, or let's say how to organize your sourcing. Yes, you have the plan, but the question how to implement that, and once you, let's say, find a solution to implement that, how to verify that this solution is actually workable. So another important thing, actually understand how your supply chain works. Again, in order to improve, to introduce some innovations in your supply chain, to find the bottlenecks there, you have to analyze that. You have to understand how it works. And for the supply chain managers, again, in order to understand where to go, how to improve its efficiency further, certainly you have to understand how it works. I mean, in details, not just in general. Experimenting and improving the supply chain, because in many cases, let's say you have an assumption how to make your supply chain better, but you have no idea how to test that. And dynamic simulation is ideal in that case, because that's exactly the environment where, risk-free environment, where you may just define the supply chain, define the logic you want to introduce there, some operations, whatever else, test it and see if it works or not. And certainly risk assessment. Again, risk is always associated with the time and randomness, and dynamic simulation in that sense is unique. So, and again, if you try to generalize all that, it basically answers the question how to implement your supply chain or how to reach the operational excellence in your supply.